Welcome everyone. Um, um, for the third technical talk that we have arranged on behalf of Communication Society Bangalore, and so this particular talk is going to be given by Mr. Kannan Babu on the topic of introduction to edge computing and green computing. Before we introduce the speaker, I would like to just highlight the kind of activities that we have been doing in the Communication Society. Being a vibrant community with both professionals and students in Bangalore, we are lucky enough to have good speakers on variety of topics. Last year, if you look at our YouTube page, in case you are not subscribed to our YouTube page, I will recommend you to do that. You can look at all the video recordings that what we have of the activities that we had done last year. And this year also on the same trend, like we have been inviting speakers from various companies, institutes for talking about advanced topics, but which is kind of toned down enough to make the students to understand, and at the same time, it is also advanced enough for the professional to learn something new in a topic which is not in your area. And so in that style, like this is one of the topics which is one of the cutting edge topics, edge computing and the green communication. So Mr. Kannan Babu will take us through those various aspects as given in the poster. And so what I want you to do is, in case you are interested in attending such topics in future, I will encourage you to join our YouTube channel that will give you the information about the post video recording information. At the same time, to receive information about the talk, we will be circulating information about telecom channel. Please subscribe to our telecom channel, Telegram channel, and that will give you the information a priori so that you can join these topics. We also publish information in LinkedIn channel, and as well we are trying to see if we can do it with WhatsApp. WhatsApp has a limitation on number of users, so most probably will go with the Telegram or some other Slack or some other channel where there is no limit of channel. So with that remark, I hand it over to Mr. Chengappa to introduce the speaker.
Thank you, Ganeshan sir, for that opening remarks. We are elated on behalf of IEEE ComSoc Bangalore chapter to introduce the speaker for today, Mr. Kannan, who is associated with Intel as Senior System Architect and Principal Engineer in the Network Platforms Group, responsible for driving edge computing with 5G and cloud native technologies. Kannan has worked as over 25 years of experience working in the domain of communication networking with deeper domain knowledge in packet processing, DPDK, cloud native technologies, and designing communication workloads to x86 architecture and optimized performance. Kannan is Chief Architect for Intel's Smart Edge program, an initiative to accelerate the deployment of edge services into the service providers and enterprise network. He is a wireless domain expert, particularly in wireless core infrastructure, driving the next generation evolution, working closely with leading service providers. Kannan has multiple patents and publications to its credit in the communication and networking area. He is also an avid sports lover, both playing games and watching it mostly nowadays, as he has shared. And he practices yoga and meditations daily and also loves to read books related to science and spirituality. So with this brief introduction, I would hand over the virtual podium to Mr. Kannan to share his insights about the edge and the green computing fields. Mr. Kannan, over to you.
Yeah, thank you, Chen. Hey, it's been a pleasure. Let me just share my content first. So hopefully it should come up in your screen. I'll go to the presentation mode if it is not showing up in the presentation mode. Hopefully it comes through.
Yes.
Yeah, wonderful Saturday evening to meet you all. It's my pleasure. Thanks for IEEE Com Society for giving me an opportunity to share a few thoughts with you all. The way that I structured the talk is starting with some basics so that I can kind of cover our enthusiastic students who will be listening to this talk, as well as some advanced topic, which I'm actively, some of the topics that I'm kind of covering at a high level, I'm actively engaged with academia as well, right, in local academia. So with that, I'll get started. I think we will have give enough chance for Q&A as well. Let me, since like we are recording, I would like to I will pause every kind of a logical conclusion of a topic. If there are any questions for clarification, I will take them. Otherwise, I will move on and we can always take the question and answer at the end as well. Okay, with that, I'll start, right? So let's start with what is edge computing, right? So I believe like in the past lecture, we must have gone through all the communication technology, especially the evolution of wireless, right, from 3G to 5G. Right now, I don't want to go back and kind of start the basics there. I believe that everyone who's listening to the talk will have at least some understanding how the wireless communication is evolved, right, over from basic voice communication to the present world of data communication, right? So now then, what is edge computing, right? Before I get into the definition of the edge computing, I'll give some small intro on how internet played an important role in all the computing and connectivity that we had, right? So when internet came up, it came up on the client server architecture. That is, anybody who wants to publish their services or provide their content, they hosted the services, right, in a server, and they connected into the internet so that anyone who has a client who has an internet connectivity, right, they can connect to the server, right? Of course, confidentiality, authentication, all the aspects came in, but the idea was anyone who wants to participate, they can freely participate. They can provide the content, the other person can consume the content. That's the primary purpose of internet, right? So now over the years, right, the contents were getting consolidated at what we call huge computing blocks called data centers, right? Now these data centers transition over the time to what we call as the public clouds, right? There are huge public clouds are available. If you look at it, you can name them, right? There are popular 7 public clouds are available as of now, right? Whether you are watching a video, you are browsing a content, a search, or you are doing chatting like social networking, all the contents are coming from the public cloud, right? So now this is the reality currently. Then what is edge computing, right? Now, if you imagine, if I move this data center grade, we call the networking, the compute, storage, closer to where the data is generated, right? So the data could be generated in the factory, in the retail shop, in the lamp pole in a busy street, right? Through a cameras. There are in the hospitals, all the machineries, right? So there are various scenarios the data are produced, right? If I move the connectivity, compute, and storage closer to where the data is produced, right? That we termed as edge computing. Now you may ask, why do we need to do, right? So what is the need for doing that, right? Before I get into those answers, right? Now, just go back the edge computing definition again, right? What we are saying is we are finding a way to process, analyze, store the data closer where the data is produced, right? So that we can enable analytics, we call the near real-time analytics and generate responses. So I can cover each one. What are these use cases, right? One by one in subsequent slides, right? So this edge computing provides a different kind of service capabilities. So for example, now you are viewing a Netflix-based content, right? Let's say you're viewing a video content. Now you can see based on the form factor of the device that you are viewing, the resolution of the content changes, right? Because this is not only dependent on your form factor, it also dependent on the network bandwidth, right? That you experience. If the content is hosted way back in the cloud, you could see the resolution of what you are viewing. It might be a 480, right? Or even 720p. If you're lucky enough, if you have a very good broadband, right? But you want to get a real experience, enriched experience when you want to start viewing in 1080p, even 2K and 4K, right? So what enables these richer viewing experience is, let's say, a provider like Netflix or YouTube or like all the video content providers. What they provide is, they called it as a CDN, content distribution network, whereas the content can be hosted very near to you. That is what we call, it's hosted near in the edge. So the moment you start hosting the content very near to you, you are eliminating the various non-linearity in your throughput or the bandwidth, right? The moment you are closer, the content is hosted closer to you, you are getting the rich viewing experience. Now, this is just one example. There are many examples out there. We'll talk about that, right? So the edge computing, as you know, we are placing a net connectivity, compute and storage of data center grade closer to endpoint where the data is generated, right? Or you can view them as the outermost layer of processing, right? Just after where the data is produced, or you can consider the outermost layer of a network, right? Where just either before the data is consumed by the endpoint, or it just produced at there and we are consuming the data right there and then analyzing it, right? So that is called edge computing. Now we got the basis of edge computing. Let's see the deployments where and all this edge computing is possible, right? So let's see where and all we could be possible, right? Now in this picture, on the leftmost side, it's where data is produced, right? It could be like, I wanted to kind of represent a subset. It is not a complete set, but it's a subset. The data is produced through camera, data is produced in the healthcare hospitals, like all the equipments are there, right? The data could be produced in the drones, data is produced in retail shop, data is produced by your phones, data is produced by your PCs, data is produced by industry equipments like PLCs, right? Data is produced in manufacturing side, data is produced in the car, vehicle to car communication. So the data is produced everywhere. Right? Now, these data needs to be, as we said, processed, analyzed, and stored, right? Has to be very closer to that. So the obvious place that you can do that is, one is the on-prem edge, which means that we define the on-premises edge if you able to provide these three factors that I have given you in the previous slide, that is network, which is the connectivity. Of course, the connectivity can be wireless and wired, and the compute, right? When we say compute, it is the processing capability that we are providing, and the storage. If you are provided at the on-premises edge, it could be a building, it could be a street pole, it could be anywhere within the purview of an enterprise, yeah, business entity. And the latency of these computing is characterized by within round trip delay of 5 milliseconds, right? So that means we classify them as an on-prem edge. But not necessarily that every time you need to host your computing infrastructure there, right? You could host it part of your network. When I say network, it can be wireless as well as wired, right? In the case of in the wireless, it is the base stations, nest aggregation units, right? The regional data centers, right? All these places where you could provide computing and storage, that becomes your edge computing. Right? In the case of wired network, it could be next-gen central office, and again the regional any aggregation points in between, right? So these locations where you can add the compute as well as the storage, it becomes a place for edge computing. Now, of course, you have the core and the cloud. The characterization of edge, we are saying if you are able to provide content, compute and analytic experience within less than 30 milliseconds, that's we are terming as edge deployment. If you want to test it out, just take your mobile phone, right? Run any speed test. You look at the round trip latency. That determines where your compute infrastructure, right? What you are doing is just a ping test, right? You can see in your mobile phone, put any speed test applications, just validate what's your delay. That you can tell you where the content is coming from, right? And you always see the lesser the delay, better your throughput is, right? The throughput plays in the wireless network the multiple other factor, but typically that is the case. Whether you are accessing the content through wired or wireless, the latency determines where the first stage of compute is there from you, right? So hopefully I able to provide you the definition of what is edge computing and where and all you could find the edge computing, right? Any questions? Okay, let me cover the drivers for edge computing, right? So then I will take few questions there. Now, the first thing, obviously, as I said, right, the edge computing, I said, characterized by anything less than 30 milliseconds, which means that what I'm talking about is the lower latency, which is definitely cannot be achieved by the central cloud, right? That's an obvious thing. Wherever you can enable the compute capability with this less than 30 milliseconds, right? That is a key driver for edge computing. One, like few examples I gave, right? In the factory, let's say that I'm doing a PCB assembly, right? Let's take an example of a PCB assembly, right? In start of the assembly line, the PCBs are getting like soldered, and then end of the line, it is getting packed, right? And there is a video camera which captures the images of the PCB that is getting assembled, right? Now, the idea here is we need to find if any of the component, especially the surface mount component, is there any defect, right? When they are doing the soldering, right? So that defect needs to be identified, and by the end of the assembly line, the PCB reaches the robo, which is taking up and putting the PCB into the packaging, needs to be informed whether it is a defective PCB or the right PCB, right? So that means you got a little amount of time before you can analyze the data, that is the captured video image, and take actions, right? If the analysis of video image and action, right? If I host it in the cloud, as we know that the cloud can take 100 milliseconds round trip latency, right? On top of that, your own compute latency adds on, you will definitely going to miss that slot, right? So that means that this kind of an use case requires that your computing infrastructure has to be close enough. That's where we call it as the low latency kind of application. Now, the other thing, what drives the edge computing is if I start generating data massively, right? And my computing infrastructure is in the cloud, I really need to move this large amount of data towards the compute, which is the uplink. As you all know, you guys have gone through the presentation of the technologies, right? Uplink is always configured as a lesser bandwidth resources, right, than the downlink, right? Because of all the public network, we have configured the higher bandwidth on the downlink because of the user consumption. But if you use the same network for your transferring huge amount of data on the uplink, that put strain on the complete network configurations as well, right? So which means that I don't want to transfer this huge amount of data to put pressure on my communication network, right? Rather, I want to handle the data locally. The other way also you can look at it, these equipment generates regularly lot of data, but whether certain data is useful or not, that we can determine. For example, if I have a camera looking at a street, it keeps on producing the video image, right? When we call the useful information is, if I'm using it for surveillance purpose, if there is a vehicle movement, if there is a suspicious human movement, right, then only I'm be interested. Otherwise, the standard video capture is not necessarily to be processed or sent back up to the cloud, right? So that means there is a chance that I can actually filter the useful information that video captured, and only that useful information I can transfer back to the cloud in form of meta information. So that way I'm saving the bandwidth, also the time that the cloud entity can process, right? So that is another key driver for this edge computing. The third, of course, is based on the data privacy, right? So for example, if I am involved in a manufacturing plant, I don't want to move any of the data, industry data, back in the cloud, right? The manufacturer guys will say, no, all the data needs to be in house. It cannot leave my campus, right, in my building. So those kind of cases, the edge computing is far more important. That's how the edge computing is evolving. Then obvious, the other case is the context awareness, right? Most of the time when you are providing any services back to the user, this, the services do not have any notion of where the end user client is, right? The context is not there, whether the connectivity, the user client is coming through a wireless network, wired network, where he is, what kind of load that access network is going through. None of the information is available to the services. So if you are very closer to the edge compute, closer to the user, you actually know about the context, the user context, right? So that means there is a greater possibility you can tune your services based on the context that you are aware. And obviously, the other aspect is that in the remote villages and remote places, your connectivity may not be reliable, right? It can be completely unreliable. In that case, you can still host the content in the locally, right? It can be like most of the contents can be cached. For example, the remote e-education, right? Where you can host it in a particular village panchayat and you can telecast the video content, the educational content all over the village, right? And then you can always, when the connectivity is available, even though it is intermittent, the edge computing can cache the contents, right? So this is one use case. And of course, the last one is the better experience that I already talked, right? So these are the drivers or key reason why edge computing is kind of now proliferating. With that, I'm open to take questions.
Sir, you are talking about this edge computing, and there is one more term that we hear, that is MEC, multi-access edge computing. So how do you compare these two?
Okay, so that is very good question, right? So what I gave you is a generic edge computing thing, which is applicable for MEC as well. So MEC is first coined by HC, right? If you look at the history of this one, is primarily targeted with the mobile network, right? So they wanted to place, let me go back to the picture. They wanted to place the mobile edge computing in the network side, right, in the wireless network. Then slowly it got evolved, just not only the wireless and wired network also has to have this edge computing. So then they called it as multi-access edge computing, right? But the original MEC intention is to place this edge computing in the wireless network side of things. It was not covering the on-premises aspects. So then the actual edge computing evolved to cover the complete spectrum, right? Both enterprise as well as the provider network. Hope that answered your question.
Yes, sir. Thank you.
Yeah. Okay. So how much time? I'm just running the timers. So I've got 20 minutes, I guess. So let me just jump on to
Till like 450 or so, 450 or so, we can then after that we can pass for questions.
Oh, okay, okay. So let me just a little bit speed up. Like if I'm going little slow, just let me know. I'll speed up a little bit. Now, just to recap, the edge computing is, as I said, one of the key aspect is the connectivity, the network, right? So the 5G, with the after the it's the data revolution started in 4G that we all know, right? Everybody has the connectivity, data network, everything happens on the 4G. 5G with 5G, with these three horizontal pillar, enhanced mobile broadband, massive IoT, mission critical IoT, right? I mean, when we say mission critical, it's nothing but URLLC use cases. I hope like you guys gone through the 5G, right? So that means these three categories have opened up the door for edge computing, because the other two pieces, compute and storage, that can move at any time, right? That's what we talked about. Once you solve the connectivity issue, right, between the where the data is generated, where you can provide the compute and storage, you have the edge computing. The connectivity was the biggest puzzle. It got started with 4G, and 5G opened up the door so that all these use cases that I'm showing here is possible with 5G. Otherwise, it is not, the network was the key issue, right? Not every time you connect the wires, not every time you connect it via Wi-Fi, because there are restrictions that we all know about what Wi-Fi can do, because it's a shared spectrum, right? So the little that you can do achieve in Wi-Fi, right? So the 5G is actually opened up the door for the edge computing. That's why we call 5G is a technology which accelerated the edge computing, right? The edge computing is not a new terminology. It always existed. It is just that when we solve the network puzzle, this has become like a multifold thing. Okay. Now I'm switching the topic to green computing. Now, previously, all the compute and storage were located in centralized form in data centers and cloud, right? So there you could the way the economic of scale and the power requirement is completely different from the edge computing, right? Which is the distributed nature. I can power up a data center in terms of megawatts. Whereas the edge computing, right? Let's say I'm hosting an edge server in a pole, right? In a traffic pole. I'm not talking about a megawatt, right? I'm talking about in terms of few watts of power, right? And if I host some edge computing in the street cabinet, similarly, I am talking about maybe 1 kilowatt or 2 kilowatt power. That's max, right? So, but if I add up all these 1 kilowatts, it can end up in like a huge megawatt power, right? But the power is distributed. In that case, if I save even a little amount of power in each box due to the distribution nature, I can save a lot of cost, right? So that means my power awareness or the energy efficiency is much more compared to data center. Data center also has the power efficiency. They have a well-defined methodology. They call track in terms of PUE, right? Power utilization efficiency, they track. But when it comes to the edge computing, it is a small amount of power and it gets distributed across the complete landscape. So even a small power that you save, that ends up in a big, huge saving. So the green computing is one of the primary purposes, of course, right? In order to be sustainable, you are providing some cost savings. That's the first thing. The second thing is policy compliance, right? Now everybody is talking about sustainable computing, right? You don't want to look at, since it is distributed, right? You don't want to power these distributed uh, equipments through the non-green sources, right? You want to find a way that all these distributed computing resources can be powered through a green energy source. So that means we are talking about renewable energy source, right? There might be some regulatory push from the government as well. So you want to look at these green computing initiative through the policy compliance angle as well. That means if I'm using a generator, let's say, right? As you know, right, a generator always produces the max capacity, so you want to use it. Whereas if I'm using, let's say, a solar-based power, right, the power is stored in battery, so I need to take care of what's my max TDP that I draw, right, in each of the servers, and what is the current that I'm like the load that I want to draw from my batteries, right, so that I can make it long lasting there. So the power efficiency or energy efficiency is much more in the angle of like in the view of power compliance or regulatory compliances, right? No, those are the two major drivers. The other two aspects is the practical aspects, how you want to do it in the edge computing. One is the resource constraint, of course, right? not like a data center where I can have racks of computes and storage. I can adapt whichever demand, right? Because I'm not constrained by any of the resources. Of course, there will be resource constraint, but that's a different scale of challenge in the data center. But what I'm talking about is for a given use cases or a services that someone is provisioning, I'm not looking for an application with the constraint of resources, right? I can have as many compute, I can rent it, I can have the storage. But in edge computing, since the space and power is constrained, I always end up in the resource constraints, right? So that means the resources are distributed. In one place, there are certain resources will be available. In other place, the resources may not be available. So I need to find a way to collectively make use of the resources wherever it is available, right? And also I should be able to accommodate all these resource constraints as well. That's one of the key driver for green computing. Now, as I said, there are hard limits on how much power or a TDP thermal limit that I can operate. So I should be able to have a policy or a dynamic policy which can work on the policy which is configured dynamically, or policy which can be changed, the inputs can be changed dynamically so that I can adapt it. I'm not saying that always I'd be operating at 2 kilowatt this one. Maybe the policy determines that, okay, I need to, this edge node is not having that much bandwidth or the traffic. So I might want to give the power to the neighboring edge node. So I will limit this edge node with a given set of power. Even though it was originally, it can operate up to 3 kilowatts. Now I can constrain with 1 kilowatt. So these kind of a dynamic policy changes, I should be able to adapt. So all these constitutes the green computing objectives, right? So now I introduced why green computing and what are the practical aspects of green computing. It's primarily coming through the three aspects, right? Distributed aspect, the constraint on space, constraint on power. So if you combine all three and include the regulatory, that's where all these aspects comes in, right? So let's get on to some actual implementation aspects, right? For that, you guys should know some basics. So I'm going to cover what are the tools are available. I start with power management, right? So when we talk about computing, we are talking about the server. So I'm just going to introduce what are the power management capabilities that exist in the server. Many of us, when we do the application development, we may not be aware of what kind of power management capability, because as I said, right, the applications are always developed for the data center or the cloud. So where these things are not that much important. Now, when the applications are developed in this edge context, there is an opportunity that we need to be aware of these aspects. You can be developing for infrastructure, you can be developing for a platform, right? Or you can developing your services at the application layer. But you should know what are the capabilities that the CPU has. So I'll just try to give you the high level, this one. Maybe my pointer is not working, but I'll just read it through, right? The bottommost in the stack and showing on the right hand side is the memory power, right? We call the RAM power. So the memory power is controlled through the advanced memory controller. So you really, as an application provider, we really do not have to worry about it. This is automatically controlled by the firmware that will enable or access only the memory channels that are active, right? The next comes is device states, right? If you are using if your server is built with any of the devices can be powered on through what we call the device states. Now, there are well-defined standards. If you are designed a PCI device, and the PCI spec provides these various device states. Then next comes is package states, right? The server is consist of a CPU, right? So the CPU can be a dual socket server or a multi-socket server, like up to 4 socket. Typically, a server, what we available a standard server is the 2 socket. So each socket can be powered on, completely powered off, what we call the package state, right? Now, then comes at individual core level. That is, each CPU consists of multiple cores, right? Based on the server that you buy, it will have n number of cores. Each cores can be individually controlled that power state. So when I say these power states, you can start with C0, which is the active state where the core is actively working on or executing the instructions. C6 is where the core is completely switched off. That means your complete power is saved there. So there are intermediate stage. The only difference is going back sleep state to the active state in various this one we call the exit, right? The sleep state C state exit. The timeline differs. If you want to transition from C6 to C0, it takes little amount of time as the kind of the processor technology improved. The transition now is in the range of lower double digits of microseconds, right? Whereas in C1 to C0, it's very negligible. It is the fastest exit that you can go from sleep to the active. So you can play around with this and with your applications, and you can save a lot of power. The second tuning or tunable element is what we call the P states. When we say P is the frequency at which CPU runs, right? We all know that higher the frequency, the higher the power that it consumes. So you can control the P states, right? Typically, when you run a server, it runs at what we call a stable P1 state, right? The P1 frequency. And you can do a CPU info in your catproc CPU info in your Linux system. It tells you what is the P1 frequency, this, that. But if you look at the frequency, if your P states are enabled, it automatically goes through what we call the lowest frequency, LFM, all the way to the P1 and above, right? That means based on the technology that you have enabled, the technology called speed select and the turbo, the frequency can go as high as what we call as the maximum performance. Now, obviously, when you are hitting the higher frequencies, your power consumption will also be high. But these things you can intelligently control in such a way that you don't want to stay in P1 at the longer time. You just enough to stay there when the work is there. Then you fall back and go to the lowest frequency is possible. And then you save a lot of power. Now, in the actual Linux world, we call these or enable like these automatic transition is provided by what we call the power state drivers, right? And you can control this governance through the governing policy. The policy itself has there, but you can define your own policy or your own thing and you can control it. Now, this is the basics of the server capabilities, power management capabilities, right? Now I want to switch on to the what could be looks like an edge stack, right? Edge computing stack. Now, just looking at the time, we are right at this 4:50. Do you want to stop right now, take questions, or let me cover this as well?
No, go ahead and finish it, yeah.
Okay. So as I said, right now, all these computes need a software stack. Now the software stacks we have divisioned as multiple layers. One is infrastructure, platform, like platform software, infrastructure software, and the application layer, right? typically the infrastructure and the platform and the relevant like extensions is provided by what we call the edge stack. So the one that I'm building, we call the Smart Edge. It is available as an open source. We provide the infrastructure element. The infrastructure element is primarily built on Linux OS, right? And then the platform software is built on top of a Kubernetes, right? The Kubernetes, as you can choose whichever runtime you want. Currently, we are enabled the Docker runtime. Like later, you can enable the CRI and other runtime as well. And then the Kubernetes, right? The Kubernetes is the basic infrastructure. We call the infrastructure orchestrator or the resource orchestrator, right? On top of that, we provide some extension in order for your any edge application developers can take advantage of this platform. Now you can have, as I said, if you are hosting your edge computing on the pole as one single server, we call the single node. In your street cabinets or your central office, if you put multiple bunch of servers, then we call it as multi-node edge clusters, right? But both, whether it's a single node or multi-node, the infrastructure layer components remain the same, and then we provide the extension agents in order for the applications to take advantage of it, right? It can start as an observability or a telemetry agent, and there are security, right? Because these platforms are remotely deployed and there is a lot of security issues. So the whole software layer has to build on what we call as zero trust architecture. Famously, you can Google and learn about what is zero trust architecture, right? So the components that we provide in Smart Edge enables the zero trust architecture. That means we do not trust anything on the component, right? The trust will be built, right? So that is the main aspect of the zero trust security architecture. So everything is enabled for you so that the application, as an application developer, you can only concentrate on your use case. In this case, how you can take advantage of the power management and the green compute, right? That's what I wanted to kind of say. Lot of information is there on the website. I have given the link. You can take a look at it and you can read it. I just want to conclude my talk with one of the use cases of green computing. There are multiple. It is there in my subsequent slide. In the interest of time, I'll just conclude with this one use case, right? Imagine this is an edge node, right? And I host a closed loop automation and machine learning based algorithms to kind of control the power, right? The predict the power, right? I would say, right? So what it looks like. In the each edge node, obviously I start with the telemetry agent, which can measure the power. The power can be measured at the infrastructure layer, measured per application layer, right? And then all this data gets fed back to this AML based inference model, right? Of course, the training is also happening, the inference also happens. Why do we need inference? Based on all the telemetry, including the power, it can predict what could happen based on the policy that we have decided, right? Let's take a small example that um, we made a policy, power policy, saying that, okay, whenever my CPU consumption goes below 40, try to migrate my application pods into the other edge node or other socket, and you can power down the complete socket. I'll just define a policy like that, right? Now, the telemetry agents are kind of capturing this information, feeding into this model, and it knows that or certain pattern, right, that I'm daily viewing, because this model is getting trained. The moment he sees certain pattern, it says that, okay, I can predict that this is reaching to a stage where I can move the application from this socket to the next socket and I can power down, because I'm sure that the traffic will reduce it, right? So these kind of the complete action can be performed by all these components that I have highlighted. Now, this is just the logical view. I'm not providing any implementation on this. The implementation, it's up to each individual. They can develop their own components here. The one which is highlighting here, the gray lines, there are open source component is available like Prometheus, which takes the custom metrics and then it publishes. But all these things have to be built by, if you want to achieve the Green Edge platform, right? I'm just giving you an idea. I'm not giving you a reference implementation, right? This is just an idea. Now, these components, uh, this is just a reference. We can talk about it. This is one of the use cases is you can decide a policy that, okay, whenever my one of the platform power, I cap TDP as 120 watts, right? When it reaches 150 watts, I will tell the descheduler to deschedule an application part, move into next node, because I capped my each server running at 120 watts. This is one example, right? The framework that I have showed, using that framework, you are going to predict that this um, server node can reach 150. It's not that after reaching you are doing, right? That's the key difference. And we are not taking after the fact. We are going to predict that this server will go to 150 watts, and then we will deschedule it so that it never hit this condition. That's one use case. The other use case I talked about, by moving the workloads, you can actually power down the servers itself, the nodes itself. You can save power, and whenever the load increases, we know that the server needs to back online, you can bring it back, right? All these things are all as an example how you can achieve the green computing. Okay, so with that, I've reached my call to action. I want you to familiarize with the cloud native edge stack. I gave a reference. You can refer to any of the edge stack that's are in the open source. I have given one example. And also familiarize with your power management features and the telemetry capabilities. Once you have all this knowledge, then you can explore the possibility for these predictions, right? For the closed loop automation. Right? The end of the day, we want to develop energy aware application, basically the edge computing. With that, I'm concluding my talk. Thanks for listening in. Thank you all. I hope this is useful to you. I know that I must have rushed through in certain parts, but the intention is to give you the glimpses, not as deep, right? So, but just enough for you to get the problem statement so that the work area is clear to you. I hope this is useful. Thank you all.
Yeah, thank you, Mr. Kannan. I think it was wonderful. In the interest of time, we will take just one question. This question from Subhash. Is the power management what you showed is like an Intel specific feature, or it is available in all processor architecture?
Yeah, that's a very good question. What I showed is Intel specific example. Some of the features may or may not be available in other architecture.
Okay, thank you. Then I would like to thank you once again on behalf of the Comstock Execom for explaining the topic in a lucid manner so that the students will be able to appreciate that. And I also encourage the audience to look at the chat box there. Mr. Chakapa has given all the subscription information for our channels. If you are not subscribed, please do so. And I invite Subhash for giving word of thanks. Subhash. Okay, maybe some technical issue. So let me do it myself, no problem. So yeah, Kannan, thanks a lot for giving this talk to our ComSoc members, and I'm sure we will come back to you again for a more advanced talk on this, like maybe for a longer duration. So this kind of open up a lot of interest among the members. I think I'm sure there'll be more questions, and those questions will address in the next forthcoming lectures. So thank you. Thanks everyone for attending the talk, and of course all the background actors who have made this possible. Thanks everyone. Have a good evening.
Thank you. Thanks all. Bye.
Bye. Thanks, Dr. Dilip. Still continuing your patronage.